we talked about the PCA. We introduced the PCA, and you remember this graph that I draw. And we said that what PCA is doing is this. It is transforming the axes that we have, the bases that we have, into those bases that if we project our data on the axis, we will get the maximum variance. So we try to maximize the variance, right? And it was kind of a linear, it is a linear transformation indeed. So we are not changing our data. We are just changing our axis. So these points are not being moved to anywhere. And you remember, we said that in PCA we try to have this minimizing L2 error, right? Which was adding all these distances will be a very small number, will be the minimum according to other combination of the axes. In order to find this direction, we saw that we have to calculate the ion values. And the first ion value will give us the first direction. The second one, which is orthogonal, will give us the second direction, and so on. And we had an example of 2D, so we had two ion values, right? We had two ion values, and we said the ion values are always orthogonal, which means that perpendicular in case of the 2D. Now, PCA is not an optimal algorithm for classification. Everyone knows about it. But like a few minutes ago, as I said, one of the good things about PCA is that in the last 60 years, in the last half a century, more than half a century, lots of people have worked on PCA. So it is a well-attacked issue. There exists lots of optimal coding regarding to PCA. So a trivial solution always is PCA, but PCA is not good if you want to do a bit more serious kind of classification. So we will talk about those methods of classification. One of the reasons that PCA is not good classifier is PCA is not paying any attention on the discrimination that we have among the data. In other words, the difference between the subsets. If we have two sets of data, two classes of data, PCA doesn't care if these axes that I am choosing really make to have big variance between these subsets. It tries to maximize the variance within the whole data. So it makes it not good for classification. We know that it's good for data reduction, and if we are applying the Euclidean distance at the end, we can use it as a classifier. So what we are doing today, we want to talk about a new method, so we don't need this one. We know what the problem is. It doesn't pay any attention on the differences that we have between the classes. So we want to talk about the data, a method which is not very complicated, but also is a good classifier. So we will learn something which is called linear discriminant analysis, known as LDA. And as the name stands, it's a linear technique. It is a classifier technique based on covariance matrix. So covariance actually helps. Look, we have variance and we have covariance. What is variance and what is covariance? What's the difference between them? Variance is looking at one data and saying how it is varying. Covariance, we said look at two data and how they are varying with respect to each other. So because it is based on covariance, it means, okay, now we are trying to pay attention on the differences or the variation that we have between the different classes. This is important because I want to have the maximum, isn't it the aim? To have the maximum distance between the classes and minimum distance within the class. So what PCA does, PCA put everything in one basket and say that, okay, let's see how I will have the maximum variation, maximum variance. Here we are talking about covariance, and we are seeing that how we can deal with that one. It is pretty old. It is pretty old. It was published by someone, I don't remember his first name, called Fisher in 1936. In 1936. And that's why that in many books, if you see, they call it Fisher method or Fisher features. So LDA sometimes is noted by this Fisher technique. So, why LDA is good? LDA is mathematically simple. Also, PCA is mathematically simple. It is robust. We can generalize it for different type of data. And more importantly, its accuracy is almost as good as complex techniques. So there are lots of complex techniques which have, let's say, the performance of 80%, and you use LDA, which is much simpler, you get 78. So it's reasonably good, and almost close. But when you compare it with PCA, it will really overbeat the PCA, because PCA is a big, well, it's not an optimal classifier, let's put it that way. LDA is based on the concept of searching for the linear combination of features that has the best separated two class. And when we were talking about PCA, if you remember, we considered two dimensions. So we said that we can generalize it to n dimension. So here we are talking about two class, binary classifier, and we can generalize it to a multi-class. Now, combination of two features, sometimes known as two variables, combination of variables or predictors. So there are different terms that we use. So we have lots of variables, lots of features, lots of predictors, and we want to say that to which class they belong. So the two classes, or class means target. Are they yes or no? Are they class 1 or class B? Are they, let's say, summon or not summon if you want to use it for the face recognition? Now, linear combination. If we have two variables, what is the linear combination? Linear combination means for two variables we have for three variables we have for four variables we have, okay, you tell me, linear combination of two variables, what do we get?
A line.
Eh?
A line.
Yes, we have a straight line. So three variables, a plane. And for four variables we have
hyperplane.
or at least how in the space geometry we call them. And if we have more, I don't know if they have the term for it. So let's see how mathematically, it's not a very complicated mathematics, I'm so sure you can follow and understand it. Let's see how we can represent it. Let's see how we can illustrate the Fisher's curve in order how we can illustrate the separability with high probability. I have to spell it wrong, but that's okay. How we can illustrate separability of data using Fisher's curve function. Assume we have x1 to xn. They are the n variables or predictors or features that we have. Then we define z to be beta 1 x1, beta 2 x2, beta n xn. So, what is the question? What is the challenge in LDA? The challenge is this. Betas are coefficients that we want to find. And what is these betas? What do we want to find them? We want to find them in a way that it will give us the best separation of the classes. The best separation of the classes. Now, we said, let's talk about the two class. Let's talk about the two class. So, because it will be easy to show everything in two class. So if I have two class, what does it mean? Can you interpret it for me? I have n variables, n data, n feature, whatever you like to call them, and I have two class. What does it mean? We divide our whole space or whole set into two subsets. So two class means that all the things that I have are divided into two. Basket 1 and basket 2. Yes, no, right? So it means some of these xi's are in class 1, in subset 1, some of them are in subset 2. Should the number be equal? In other words, if I have 5 in class 1, should I have 5 also in class 2? Goes on? Suman?
No one's.
No. We can have 1 in class 1 and 1 million in class 2. So we don't know about the numbers because it doesn't mention that they should have equal number of vectors or features. So we divide the subset, we divide our sets into two subsets. If we say that we have two classes, can you tell me that what is an equivalent name for it? Someone said something? Be a man. What? If you have only two, yes, no, what do we call it?
Logical.
It's binary decision making. Two class means binary decision making. So we do a few steps. We have to follow these few steps together. Step number 1. We find mu1 and mu2, which are the mean of subset 1 and 2 respectively. So we have two subsets. We divide our whole set into two subsets.
Do we randomly do it, or is there a...
No, well, I give you the data, and there are two data. One of them is data blue, and another one is data red. So it means we have two classes, two subsets. And what we want to do is, we want to actually find what are those two subsets. I have data and I want to classify to two classes. One of them is class 1, one of them is class 2. One of them is yes, the other one is no. Remember, here is another difference between PCA and LDA. In PCA, we said that we want to see the maximum variation. But here, we said that we want to divide it into two sets. We want to find the two subsets. The class, we have two classes. We want to find what are those two classes. So we are doing the labeling. In PCA, we are not doing the labeling. Yes, sir?
So the data is classified before then? Or
No. The data is not classified. Right. We have the training, which we know what are the labels.
But we know what are.
Yes, and then we want to come up with an equation, which if you give me one data, I have to find out which of these classes it has to go. So right now, we want to see that how I can represent these sets in a very variable, separable form. Now, and at the end, I want to get back to this point how, again, the PCA and LDA is different from each other. So we have these two subsets, and these two subsets, when I look at them, maybe they are very inside each other. The question is that how I can find a way to, when you give me data, I can surely say that this data belongs to this class or belongs to another class. So we want to see how I am doing this type of transformation that we want to see. Calculate the covariance matrix of the data called C. then the score function is, now C is the covariance of the whole data. We are talking about the big data. Calculation of C is not very easy, so we will see how we can calculate C. In the real life, your computer will calculate not C, but the thing that I will write in a minute. But computer will calculate it. It's not very easy and handy. So the shape of the score is S beta is equal to where the beta is, I have erased it. It was x1, beta 1 x1 plus beta 2 x2 plus beta n xn. So we put the betas into a vector form. So it's a vector. Mu is the means, C is a matrix, and the T, operator of T, it means the transpose. I'm so sure you know about that. So what we want to do, we want to find beta, and we want to find the beta in a way that the classes, the two classes that we have, has the maximum separation from each other. In order to calculate this S beta, the mathematicians have said that we can represent it as S beta is equal to divided by now, what is Z? Do you know what is Z1? You remember that we said that Z is this. Beta 1 x1 plus beta n xn. So can you tell me that what do you expect the Z1 to be? Linear combination of those x which are in class 1. Z2 is linear combination of those x's which are in class 2. And beta multiplied by those mu1s means that the mean of class 1 minus the mean of the class 2. So they are an equivalent terms to each other. And this one, what we are calculating is actually variance, which is actually variance of within groups that we have. Variance of Z, variance that we have for within the groups, but groups of Z. Can you tell me that what it means? Variance of groups of Z. There is another term which you are very familiar with that. Variance of within group of Z.
Difference between the real number and complex number, but imagine
What?
of the
No, Z is not is a real number, it's not a complex number. It's just Z for the sake of Z, it's not a complex number.
so the distance between the term of the group, which
So what does it mean?
the covariance of between
What does it mean? Sigma square of Z within the groups of Z. What is the variance? What is the variance? What you said, Fatima, is correct, but this is not what I'm saying, you know. What you said is just reading this statement, but this has an equivalent. Let's get back to lecture 1. We talk about good data, bad data, right? Or good feature, bad feature. What is a good feature?
That has a lot of variance.
What is a good feature?
Small within class distance.
It has a smaller within class distance,
Big.
between class distance. So between class discrimination. So we know within class and between class. Can you tell me that what is this? It talks about the variances between Z's. So it is which distance?
Between times.
Between class distance. So we have the between class distances in here because it talks about the variances between z's. And each z means we have two class z1 and z2. So this is the S-score function. So what is the aim? Given the above score function, the aim is to, what is the aim? Is to find those betas that maximizes the separation between classes. And again, mathematician has solved this optimization question which can be solved by, they have find beta is equal to the covariance, the inverse of covariance matrix multiplied by mu1 minus mu2. Covariance matrix can be calculated by 1 over n1 plus n2 multiplied by n1, c1 plus n2, c2. What is c1? What is c2? c1 is the covariance of the set 1, c2 is the covariance of the set 2, n1 is the number of elements that we have in the set 1, n2 is the number of elements that we have in the subset 2. C is referred as pooled covariance matrix, which means that the covariance matrix of all data which are in the same pool. Betas are known as linear model coefficients. Now, mathematically, it will be continued by saying that in order to assess this discrimination, one way is using the Mahaboulos distance between the two groups. So, one way of assessing the coefficients of the discrimination is to calculate the Mahalanobos distance between two classes. And experimentally it has been shown if we calculate this distance, the distance greater than 3 means the two group are well separable with almost no overlap. In other words, when we say that this is subset 1 and this is subset 2, when we draw a line in order to say that under the line or on the left of the line we have group 1 and then on the other side we have the group 2, there is no point of group 2 inside group 1, or there is no point of group 1 inside group 2, so there is no overlap. And this number has been experimentally found. And how this Mahaboulinus distance is calculated is in this form. Delta S squared is beta transpose multiplied by mu1 minus mu2. So if we have, now, I'm doing a numerical example in order for you to see what we mean is this. After we calculate the beta, after the optimization has happened and we calculate the beta, we will put it into this equation. You already know what is mu1, you already know what is mu2, you already know what is beta. So you multiply and you get a value for delta squared, which delta itself is the Mahaboulinus distance. We look at this value. If this value is 3 or above, it means that your data is well separable. There is no overlapping, no problem. If it is less than 3, but close to 3, it means that it's still separable, maybe one overlap. But if it is, let's say, 1 or very smaller than 3, then it means that you draw a line. You say that this is group 1 and group 2, but you are increasing the probability of misclassification. So overlap means this. You can read it as probability of misclassification. We understand that in the computer science, you really don't sit down to write any of those things. Many of these things are actually being calculated. We have in computer, we have lots of live mathematical libraries which you can simply call in and it will calculate all of those terms for you. Now, the question is this. I have calculated beta. I can look at the Mahaboulinus distance. So delta is Mahaboulinus distance. I can look at this one and say that, wow, what a good data. They are very well separable. But the challenge is this. Now, you have your data, you have drawn the line, you know that which data, which group is A, which group is B. The challenge is that I give you a new data, one value, and you have to tell me that which class it belongs to. In other words, we are testing that. Now, how can I understand that we are in group A or I am in group B? One way is that I have the data visually drawn, and I have the line which, why line?
We have 2D data.
Yeah, because I have only two classes, so I draw a line. If I have 3 classes, I will draw, let's say, planes, which of course you can always map it, also draws 3 lines. Now, here I have the line, I have all the data, and whenever you give me my data, I look at it and I see that where in this graph I have to put it, and I say that, okay, it's in group 1 or it's in group 2. But not all the time, the data that we have is very cool or is small enough to draw it. So what we need to do, we need to see that how we can find out in which group we belong to. In other words, there is a mathematical formula which you have to use in order to check whether you are in class 1 or you are in class 2. And this formula is this. Again, in computer, it calculates. If you use MATLAB or LDA, it already does that thing for you. For a given data x, if the following equation, well, I said equation, but it's inequality. If the following inequality holds, we are in class 1. We are in class 1, and the equation is this. Beta transpose multiplied by x minus mu1 minus mu2 divided by, plus mu2 divided by 2 is greater than logarithm of p of c1 divided by p of c2. On purpose, I have not written that 1 and 2 as an index in order not to confuse this one with the covariance matrix. C1 means class 1, C2 means class 2. How can I calculate? How can I calculate the probability of C1? Eric, how can I calculate PC1?
PC1 probability
Yes.
of point being in C1.
How can I calculate it? This is the probability of having a point in C1. Yes, this is true.
Find the similarities.
Ellen, do you have any easier way?
Number of C1s divided by the
Number of elements in C1 divided by total number of data. If I have 100 data, 60 of them are in C1, so it means PC1 is 0.6 and PC2 is 0.4. Right? And it is very obvious. It's very obvious. If the probability, if I have more points in C1, the probability of the data that comes and goes to C1 is higher. Right? Let me show you some data. This data that I will draw and I will write some numbers are from a real example from business. But I don't write the question. I want you to just see the numbers. Then we will go to the computer and the presentation, and we will see how in, let's say, MATLAB we can do it, how graphically we represent the data and so on. So there is a sample of 100 data which has been collected by some, let's say, business people. And they have the blue and green data. And when we withdraw the line, it will be like this type of line. Then Z is equal to beta 1 x1 plus beta 2 x2. For the data, for that data, they have the value of x, like whatever the x-axis means and whatever the y-axis means, so they can calculate the covariance, they can calculate the means, so they can simply substitute into the formulas that I just shown. And after that, when they are calculating the delta, they will get this value. They calculate the delta, and they find that delta is 2.5. Okay, who wants to interpret it? Okay. For this data, they have calculated the luminescence distance to be 2.5. What does it mean here? And I want you to relate it with this graph that we have. You are not cared, probably, right? They are
Not separated enough.
not separated enough. So what does it mean? Not separated enough.
You said that the distance has to be larger than 3.
No, I didn't say it. So that experimentally they said that if it is 3, it's separable enough. But what does it mean separable enough? Tell me through this graph. Abdulaziz? There will be overlap. Very good. Tell me in this graph, what does it mean? They are not separable enough. They have overlap.
Then some values of C1 will be in C2.
Tell me about this graph. It means, let's say blue is C1, green is C2. So overlap means, do we have overlap? Is it true? Okay, you cannot see. Anton, you can see. Do we have overlap? What is the meaning of overlap? What is the meaning of overlap? Means some of this one, for some of the group 1 as Abdulaziz says is in group 2. Do we have overlap in this example?
Yes.
Yes. Look. Look. So we have overlap. We have overlap. So if I give you a data value, let's say x is, I don't know, alpha and gamma as a pair, 2-dimensional. How do I understand where do I have to put x? Should I put it in green or should I put it in blue? How can I understand it?
Compare it with green and blue.
Okay.
Calculate it and see if it's
Calculates it. If I didn't have the graph, looking at the probability, what else? Can I use this formula? Certainly. The answer is yes, I have to. I must use this formula. One way is looking at the graph. And if you don't have the graph, or the graph is too crowded and complicated, which you don't know what the axes are, then the only way is that you put your value in here, and you calculate, and you see that if the condition is satisfied, then you are in class 1. Otherwise, like in equality or less than, then you will be in class 2. So, this is the general idea of LDA, and we have seen the general idea of PCA. PCA try to define the direction, which in that direction, if you walk, you will see that you will have the maximum variation within your whole data, whole pooled data. In LDA tries actually to give you the line, which if you project your data on that one, you will get the maximum variation between the classes. So you see LDA, if you remember from the Fisher-Escore method, LDA start to pay attention on what is the differences between the classes. This is what is missing in PCA. That's why PCA is not an optimal classifier, because PCA doesn't care about the label. PCA look at you and tells you that for all this data we have this maximum variation. Having maximum variation is not necessarily means we will have the maximum variation between the classes. So having maximum variation may not means results into have a better classification. Now let's go to the slides and see how our slides are dealing with this.
when you're doing that, can I ask?
Yes.
I didn't really understand how we get still these two classes. Like, what are these two
No,
classes?
okay, these two classes is this. for in case of two classes, what happens is that we calculate the value of betas.
But do we just
And
like we have data set and we just how we get these two classes?
No, we have the, imagine we have two faces, two classes, because we have only two classes, okay? And I have lots of your faces and lots of his faces. They are all in here in this pool. Now I want to say that I draw a line, and anything above this line is limit, otherwise it's not limit. How can I draw this line? For two classes I will find two betas. For here, if it was a two class, I will get beta 1 and beta 2. And it will be a line, beta 1x plus beta 2y is equal to, let's say, 0.
But I have to know these classes to
Yes,
calculate
you
beta.
have, no, you have it, you have one. These are all these dots. You have the dots. You know, you have all these dots. Okay? This, look, the blue dots and the green dots are given to you. Question is,
But I know that these are like different classes.
yes, of course you know that they are different classes.
Okay, well, so I was asking, how do I get these
Well,
classes?
yeah, but I do not give you all these blanks and tell me that how many classes we have. Here you have only one classes. But we already know that we have two class situation. And sometimes, look, I have talked about binary. Later I will talk about SVM, and you will see that in MATLAB we have a binary SVM. And we can actually generalize a binary situation into a multi-class. How can we do that?
We just compare it to the others.
Yes.
You know, one or the other.
Imagine I have this binary class and a classifier, and I want to classify three classes. How I do it? Class 1 in not class 1. And not class 1 means class 2 or class 3. Right? Because here, not class 2 means class 3. It cannot be class 1, because if it was already going there. So if you have more than two classes limit, you can say the limit and not limits. So we know that we have two classes. And the question is that how I can draw the line. If I have only this dot, then I cannot do it. Remember when I was talking about the PCA? I have only one color dot, right? One color dot. And PCA cannot tell me that how good I can separate this one into two classes. That's why that after PCA, you will see in the code we have Euclidean distance, and we look at the distances, and we say that if distances are very close to the line, let's say I say class 1. If it is more than this value, it is class 2, and so on and so on. Okay?
I guess the question was like if the training data is pre-classified already.
No, they are all called supervised learning.
Yeah.
In other words, when I am training, and I already know I have two classes available.
So they're like already.
In other words, the colors are already
they're
there.
labeled, right?
Yeah, and they say that if you look at the differences between PCA and LDA, one of the things they say that in PCA data are not labeled. It means that we don't know how many classes we have. Here, or you can tell the PCA, hey, I already know how many classes we have, but it doesn't care. It doesn't introduce anything new. But in LDA it does. That the question solved?
Yes.
Good. Where is your input control?
Yeah, and backside.
Yeah. It's hiding. It doesn't want to be used. Please, don't play with your mobile phone. And more than that, please read all the supplementary materials that I am providing in the module. Now, in the module, you can see that I have provided the paper has been published, if not mistaken, about 10, 15 years ago. And it is a very, very good paper comparing PCA and LDA. 15 years ago, still people were working on this. PCA and LDA are like about 50 years old. So 15 years ago, when people are still working, it was very amazing. Not that much fun. But if I fell down, it would be very good prank here. Now, another document that I have provided in the module is something about FAR and FRR analysis. False acceptance rate and false rejection rate. You remember I actually talked about them, and we said that if you make a system and your system meant to work in the real life, then you must do FAR and FRR analysis. Otherwise, you cannot really say that, hey, the system works perfectly. Because you will do a homework, right? And in the homework, we will do the PCA-based face recognition. You can do this test. Grab one of your friends who is not in the database, take his or her photo, and give it to your system. And you see that your system will say that, oh, this person, let's say, is, I don't know, sharp. Okay? Why it does it? Because it looks at the closest distance and it picks the minimum and declares it. Whereas theoretically and practically actually, we want, if the person is not in the database, it should not be recognized. It should say that this is not a person. That is where the FAR and FRR comes into place. I don't think that I will, I have planned on talking about so many other things, so I don't know if I will have time to get back and talk about FAR and FRR further. If we have time, I will do it. If not, I am recommending you to read that supplementary material that I have provided for FAR and FRR analysis. Those supplementary materials, which I am not talking about, you will not be, of course, responsible for that in the exam. However, if we have time and I will get back, it means you will be responsible for that in the exam. I have also put one sample example for last year final examination in the module. So you can go and check what was the last year final exam question. Then you can decide whether you want to withdraw the course or not. I have also put the dates of the exam. You can see that one of them is on 28th, the rest of the December. I think was it 28th that I acted or not, but I made it 28th. And then 2 will be after the new year. Also for that, the other course, the robotic technology, they have put the dates also in module. The protocols are not open yet. I will send it to Kyrie so she can do it so you can register for the final exam. Yes?
In module it says 29.
Okay, it was 29. 28 will be the other exam. Okay. So I will quickly go over the slides. You already have seen the slides. Remember, the mathematical proof, how we get to that point is not, it's important, but you don't need to prove anything in the exam. For you is, what is important is that how to handle this information and how to interpret it. Now, when we are talking about LDA here, you will see that there are actually another way of representing LDA, more complicated version, because we have done it for 2 classes, so it was easier to handle. We will see that if we have a multi-class, how we can handle the formulation, but still, the concept will be and is the same. So, we are still in the linear methods. You have learned PCA. We have talked right now about LDA. I am planning to talk about ICA, which is called independent component analysis. It is much more complicated than PCA and LDA. Computational complexity-wise, it's much more. It needs much more computational complexity to do it. Last year we didn't talk about it, but this year I might talk about that one because it's good to know. Now, the LDA was working in general in this form. when we had a PCA, we try to draw a line which is passing through this data, and we said that this is that direction. I mean, not necessarily color to that one. This direction is that direction that we will have the maximum variation of the whole data. In LDA, we don't do that. In LDA, we don't do that. Our aim is to find such a line which separates our data, that if I am conducting some type of projection like that, I will have the maximum variation between the data, between the Zs, right? As you can see here, we have one overlap between my data, so it means that it is all right. If you look at the value of the Mahaplus distance, it should be, let's say, 2.9, and so on. So aim here is to find the maximum variation between the classes. In PCA, we were not talking about classes at all. We want to have the maximum variation between the whole data that we have. Now, in that case, if we have multi-class, this is how actually LDA looks like. So the Fisher score function, if you want to calculate it, will be this. So this is our S-score function. And then when we are talking about S-score function, we will have two types of distances that are being introduced. One of them is within class, the other one is between class. Now, you tell me, which one should be bigger, which one should be smaller, or what is our ideal case?
So within class distance is small, and this one is big.
Yes, so this is our aim. We want to find out that this distance will be small, and this distance will be big. Now, if you go to the slide, it tells you that what are each of these X and S and these means, but at the end, the Fisher S-score function for multi-classes can be defined in this form. The between class and the within class. And the aim is to maximize. Forget about the Fisher. Forget about everything. I have a function which is written in this form. And I want to maximize this. How can I maximize this? Number A divided by number B. How can I make the result very big?
B small.
They want the numerator big, denominator very small, right? So I want this one to be big, this one very small. So it means that between the classes big, within classes very small. If I do it, I will start to maximize JV. So the whole aim is that to maximize the JV, which will automatically result into increasing the between class distance and decreasing the within class distance. Again, mathematicians have nothing else to do except solving this, so they find out the solution. The solution will happen if this equation is true. If this equation is true. SV multiplied by V is equal to lambda SWV. So we can calculate the value for lambda, and we can get what is the line that we need to draw, what is the plane or hyperplane we need to draw in order to separate our data. Now this is, here we don't talk about the two class, we talk about n class. That's why the formulas will become nastier, more complicated into when we want to display. Now this is a good graphical. I love this because it shows how the difference between the PCA and LDA is represented. PCA, as I said, will go a line. It's a line which usually goes through the data. And it does not care, I'm repeating myself for the 10th time, it does not care if you are blue or yellow. It looks at the whole of this data and says that, look, on this line, if you project all your data, we will have the maximum variation. But in LDA, we will come out, we can interpret it in this form, we will come out with the projection, with a line, which if you project your data, you will see that the blue data and the yellow data will have the maximum variation among themselves. In other words, the Z1 and Z2 will have the maximum variation. I mean, this is again an example. It seems they are perpendicular, but not necessarily. We can come up with an example which this direction is the same as the direction that the LDA is also suggesting. If you project your data, you will have the maximum variation. But this is only one single example. I mean, you cannot generalize based on that one. If you are using MATLAB, MATLAB has a comment called classify and also fit discrimination. And fit curve discrimination and classify are those which, if you play with the parameter, you can enable LDA and conduct LDA. Also, if you go to the math work, you can see the code which is for LDA. So you can see the different parts which we discussed today, or in the formulas, the multi-class ones, you can see how they are being calculated. I do recommend you to go over this one. Again, last year, as I mentioned before, this was another homework which people have to do. PCA, when it is finished, they will apply LDA and they see that what is the performance, how the performance is being changed. But because it's only plug out PCA, plug in LDA, so you can do it if you like to, but it's very obvious that LDA will overperform PCA simply because naturally LDA have been designed to be a classifier, but PCA was not being designed to be a classifier. Good, I got the slides finished very quickly. And do you have any question?
Could you go one step back?
Sorry, one slide back?
Yeah. It's confusing me.
Ah, yes. It means that only one person is not listening. That's very good.
That's very quick. I have a question. Why do people use that PCA? Why is it good to use PCA instead of that?
No, it's not good to use PCA.
But
the question is that why people are using it? Because it's incredibly fast. Because you don't need to worry about if it is optimized or not. And it's already been optimized. So it's a very well attacked, very cheap, very well optimized, so you can just put in your code and run it. And for many of the purposes that you do, you don't need to have, let's say, but LDA is also similar to PCA from that perspective. But you don't need to have very, very high accuracy. It recognizes you. The bad thing about the PCA was this size, light changes slightly, everything will be destroyed, but still you don't care because you have to log into a very low security laptop that you haven't produced by, let's say, X company, okay? So PCA is very, very useful from that perspective. Otherwise, if you go to the border control, no one is using PCA. They will laugh at you to use PCA. Even nowadays, if you are writing a face recognition algorithm, and if you compare yourself with the PCA, the reviewer will laugh at you. And they say, you are really, everyone is better than PCA. So why do you compare with PCA?
But why, I mean, it doesn't seem that LDA is much more, expensive, or why shouldn't we always use LDA even more?
Well, do you know why most people are using PCA? They don't use it as a classifier. I still use PCA for reducing my data. So you have to look at what is the aim of using PCA. PCA is still very useful if you want to reduce your data. Or imagine you have another very clever classifier, but in order to do the classification, you need someone to tell you that what is important, what is less important. Here, PCA. What PCA does, the direction tells that this is important, this is a little bit less important, this is irrelevant. So you can look at those directions and have some better idea, maybe use some CNN or some fuzzy logic in order to conduct further. So PCA was never aimed for classification. It was used for data reduction, it was used for feature extraction. People still are using the PCA or MPCA, but it happened that it was also for classification. People used it. But again, one of the reasons that we still use it even as a feature extractor is that it's very, very well attacked. But there are still lots of other algorithms which are very well attacked, very well optimized, and people are using them. So,
Are LDA and PCA combined?
Are
LDA and PCA combined sometimes?
Well, you can somehow drive LDA through PCA. But what is your aim? What is your purpose of combining them? If you want, I don't know if someone has combined it. With high probability, the answer is yes. but it was not something that I'm being interested to follow to see if someone has done it or not. Read that paper which I have provided as a supplementary material. Maybe there are some examples actually when the people are combining it.
But as you said, they can be applied first PCA and
Yeah.
then reduce the data.
Yeah, you can change the do the transformation and then apply LDA. I don't know if you gain anything out of it. I mean, it's like this. I have my data. Can I multiply everything by 2 and then conduct? Yes. Will it be useful? I don't know. Usually people take whole data and subtract everything from mean. Nothing will be changed. The idea, the whole thing will be the same, but the numbers are smaller and easier to manipulate. What will happen if I don't do it? Don't do it. I mean, again, as I have not read any paper that they said we apply PCA followed by LDA and we gain something very good. Maybe it exists, but I don't know. It's of my interest. I never researched for that. Do you have any other question? So homework for 29 days right now? So, thank you.